We're good? All right, thanks. Good morning, everybody. So as Ron mentioned, today we're going to talk about some options on how we are going to go about reducing usage of SMI. How many of you here are familiar with SMI? Pretty much everybody, I guess. Yeah. So we all know and understand that SMI is probably the root cause of all evil in the firmware world. And getting rid of that's probably a good thing, but let's get the first step going, right? So if you look at just a primer here, right? SMI, we all know, is a broadcast in nature. It's got a lot of security concerns because it gives you a lot of privileges once you get in there. You have all the registers, locked registers can be accessed. You can have all of memory that can be accessed. And it's broadcast in nature, so it stalls all the cores. And we go in there for however long it takes to do the job and get out. OS has no clue about it, right? And it's a black box, so it doesn't know, you don't know what's going on in there, right? So you can't see it, you can't audit it, you can't debug it that easily. So let's look at the current view of SMI, right? OSs don't invoke SMI directly. They have an abstraction layer through ACPI. So the OS, if they want to do any platform-specific work, then they invoke an abstraction interface like ACPI or runtime services. And from in there, we drop into SMI, mainly because we cannot do much in ASL anyways, right? People who have done ASL code can see that it's very cryptic, very primitive in nature. You can't do a lot of things in ASL. And we can't do even ISA-specific things because ASL is architecture neutral. If you want to do MSR accesses, or if you want to do instructions such as sfence or CLFlush or pcommit, we can't do anything there in ASL. So people drop into SMI for convenience, right, in this case, and do the work because they need a native code execution context to assist the ASL code, right? This is one usage of SMI. And the goal here is to keep the abstraction interface the same. OS still sees the ACPI tables. But underneath that, instead of dropping into SMI for a native code execution context, can we give alternate means for doing the same thing, right? And that's the goal for today's presentation. So let me divide this into 4 different categories of SMIs, and we're going to basically focus on the first category. So we all know that there are software SMIs, we just talked about, where you write to port B2 and invoke an SMI. And then there are hardware SMIs, which means we have platform events, errors, right? Thermal events, GPIOs. They can fire SMIs as well. Now, the software SMIs, we can split them into 2, those that require privileges and those that don't require privileges, right? And when we looked into it, the only 2 SMI handlers today that we have that require privileges. By privileges, I mean that things that you can do only when you are in SMI, right? Or BIOS update and variable updates. So those we'll address a little later, but today's focus is mainly on the software SMIs that don't require privileges. And we are going into SMI only for convenience. And when you look into a lot of these usages today, we have almost 50 of them today for a variety of reasons, RAS reasons, for NVDIM reasons, right? We have a lot of them today. So we can try to get the low-hanging fruit, get it out of the way, and go after the rest of them. Now, on the hardware SMIs, we are looking at doing it through an out-of-band RAS. Most of you, I think, are involved in the conversation. I see Sumit there. So we basically have some engagement going on using out-of-band RAS for hardware SMIs. And let's go talk about the software SMIs today. So the question invariably comes up, right? Whenever it has a discussion, people go, well, then why can't I do a driver model, right? And that's a valid question. We tried it a lot before. And that's true that a lot of things today we are doing in SMI, if they are architectural in nature, meaning if they are sort of constant in nature, we should move away from SMI and into a driver. right? But a lot of things require intimate platform knowledge. For example, when I get an error, mission check banks gives me the system physical address, right? And I need to translate it to the actual DIM address, which socket, which memory controller, which channel, right? Which rank, bank, column, row. All these things depend on variety of schemes, interleaving schemes, whether you're in hemisphere mode or not, right? So a lot of things are intimate platform knowledge that the drivers don't want to carry, right? And because it changes every generation. So the ideal thing is for the platform to carry the information along with it. And the best place is the BIOS, because BIOS moves with the platform, it travels with the platform. And here are some examples of what we tried earlier. Picture plugin, address translation, we tried doing these things in drivers, but OS vendors say, you know what, we don't want to carry all the silicon knowledge in the drivers. So here, BIOS, you know more about the platform. Give me a DSM interface, I'll call you, you do it for me. Right? For NVIDIA, we tried some ACPI infit tables to abstract it out, but again, OS vendors came back saying, it's too complex, just do it for me. Right? So these are the reasons why we have to have some native code execution context in runtime, right? And SM is not the solution. So let's go to the actual proposal here, right? We talked about it in the OCP Regional Summit last fall. And today we're just going to do a case study, take one example, and basically show a video demo of what we did there. And so if you look at what a platform runtime mechanism is, it's basically a way to call into a native C execution context, like a runtime protocol from ACPI. Right? So we need a small bridge driver, a generic write once bridge driver. What it does is basically loads on a ACPI device object. That is a standard mechanism, been there for, 20 years now. So the driver binds to a device object and loads on it. On the other side, it knows how to call into a runtime protocol. That's also industry standard, been there forever. Right? So both are known mechanisms, existing mechanisms. All we're doing is that putting them together. Right? So now, from an ACPI context, instead of writing to port B2 going into SMI, I'm going to do a notify on the device object, which will do an event notify to the driver. Driver turns around and calls the runtime protocol. This is at a high level. This is the basis of what we are proposing here. Okay. So the case study here deals with doing error handling, right, using this PRM mechanism. Today, what happens is when we do error handling, we can fire a CMCI, for example, if it's a correctable error, fire a CMCI directly to the operating system. But the information in the mission check bank is not sufficient for the OS to make any meaningful PFA algorithms or find out the fru on which DIM the fault lies. So we have this firmware first model where we fire an SMI first, go into SMI handler, go read all the registers, do all the calculation, then they build a table called HEST table in ACPI, and then we notify to the operating system. Right? That's today's model. And what we're doing here is basically doing the exact same thing, but using PRM. Right? So we are firing a SCI and on a correctable error, and the SCI will land us in ACPI context. We call into a PRM from there, which is a runtime protocol, which will build the HEST table and fire an SCI to the operating system. Right? So this, what I'm showing here today is basically on a Mount Olympus system. And let's go here. So this is today's model, right? So this is what happens today. And let's see what, we are doing it in Mount Olympus now. So that's going to be a video here. On the right-hand side, you will see SMI count. Okay? And this is a Windows event log. We are injecting memory correctable errors. And as we inject memory correctable errors, you will see that we're printing out whether it's SMI or PRM on the left, and the SMI count will keep increasing. So if you look at the event log, we will see the events show up there when we inject the errors, but the SMI count was increasing. Right? Now, this is the PRM-based mechanism. Same thing, but using SCI instead of SMI. Right? So here, again, same SMI count on the right, and we're injecting memory correctable errors. Right? And as we invoke PRM, we are going to print it out here. And SMI count is static, no additional SMIs. So we are doing the whole thing without any SMI. Right? And if you refresh the event log, you're going to see all the errors show up there. So we can do the whole thing, right, with a firmware first model without using SMI. Now, this is only for demo purpose, or I shouldn't say demo, but a case study purpose, right? We can basically target any DSM. For example, if you go to pmm.io, there are a bunch of DSMs to support NVDIMMs. Those DSMs today drop into SMI. Those can be migrated out to the PRM module. Right? So this case study basically shows a correctable error. There are other ways to handle correctable errors using an out-of-band mechanism also, the error pins. And we are working with a lot of stakeholders on getting that working. Right? So this is not Intel's recommendation that we do it this way. Right? If an out-of-band mechanism is the best for you, that's the probably right direction. But for any software SMIs that we talked earlier, that drop into port B2 only because they want to see a native code execution context, this mechanism works really well. Okay, so basically, we do have the source code in GitHub, and this is a very it's a sample code, right? It's not a fully functional code that I just showed you, because there are some licensing issues before you put it out, and we will do it soon. But this is basically a baseline on how to go about doing this. So we have the sample ASL code in GitHub, and we have the sample PRM handler in GitHub. So you can please, you can go ahead and take a look at it and see how it's being done, and waiting for feedback from you all, right? Now, one thing when you go into the GitHub repo and pull it out, you might see that we are hiding the PRM handler behind the get services variable call. The reason is that today Linux does not allow you to call into any other runtime services other than get set variables. Linux is blocking it. So we're working with the community to basically make this more architectural. But for now, we are basically hiding the PRM handler behind the get set variable services. So when you see that code, then don't get confused. Why? Right. So that's pretty much what I had. Any questions? Any suggestions, feedback? Yeah.
I mean, do you see it ever being possible to get rid of every single use of SMM?
Let's go back to this slide here. So I see that the category 1 handlers, they can all move out to PRM today. Okay? There is nothing stopping us from doing that. Software SMIs that require privileges, meaning firmware update or variable services, there are ways to go about it. We are investigating the right options. The firmware update will be through like a capsule mechanism where you stage the image in memory and then you reset and pick it up on the next reset. So that's the existing mechanism, right? You don't have to update in runtime. And then the variable services, a couple of options. One is, can we do it out of band, right? Because in a cloud environment, everything is serviced out of band. BMC is the entry point, right, for configuring the system. So can we provision it out of band, which means can the BMC be a repository for the setup variables? Right? And Redfish provides schemas for that, to do that. So that's one option we are investigating, right? And for hardware SMIs, for both the RAS features that require privileges and those that don't require privileges, we can go the out-of-band mechanism. So when we move all the RAS handling to the BMC, then the need for doing SMI goes away. Okay. So the first one, we can do it today. We are enabling the the ecosystem with it. We have there's no technical roadblocks in getting there. Right? These things we are working with the stakeholders because it requires the BMC to know about the platform. Right? BMC has to today. BMC doesn't understand the platform topology. Doesn't in the sense that doesn't know how to read the memory topology or the interleaving schemes and things like that. And the BMC might be taught to do how to do those things. So this mechanism, the PRM mechanism, is not Intel specific, right? Because it can be done on any platform. So this is basically something that we are contributing to OCP, OSF. Yeah, Malik.
First of all, awesome work, Sarathy. Really nice to see some of the SMI handlers probably potentially going into the PRM space. Some SMI handlers, we try to also invoke the application threads. I mean, sometimes the Monarch can also call application threads. In the PRM space, is it possible, or do you see a pathway where multiple threads can be?
Yeah, that's a good question. So PRM by nature, we are making it single-threaded, because today, if you look at ACP-ACA, it takes a global lock. So the whole thing is serialized. So let's say you invoke a DSM. One driver is invoking a DSM. The other DSMs are blocked until the first DSM is serviced. And we are adding basically some serialization logic in the ASL code so that we take a lock. And once the PRM is done, the next PRM will take over, right? Will fire. So, but the PRM handler is nothing but a ring zero code, so which means it is interruptible. So it can take higher priority interrupts. It can take other interrupts. You had a question.
Thanks for the good work. I have a question and a comment. So first is that to make this effective PRM, some of the hardware platform design change or principle needs to be there. So the question is, for example, right? You talk about the correctable error handling, right? Now instead of it creates a SMI interrupt, it actually activates the error 0 pin, and then right it does fire a GPIO through PCH, right? So that would require some platform design change. So the question to you is that for Cooper Lake reference platform, right? Do you plan to do that platform design to accommodate PRM?
Right. So basically, to repeat that question, right? So are there any hardware changes required to accommodate PRM? Right? This is the basis of the question. So the short answer is no. What we showed here is just a case study on how to do correctable errors. But if you are moving DSMs, if a DSM interface being called by the OS, and you underneath the DSM you're invoking PRM, there's no need for any hardware changes. Right? It's a software concept. This particular case study is using an error pin to generate an SCI, right? And depending on how you want to handle correctable errors, you can wire it to a BMC to handle them directly, or you can wire it to the PCH. Now, all of Intel's PDG, platform design guides, they have this wired that way. It goes to the PCH, right? And all our reference platforms are wired that way.
Right. So let's say for the number 4 to work, we need the SMI to be wired to BMC.
This one?
Yeah.
Yeah. So for this one, we are wiring all the error pins to the BMC, right? Error 0, 1, and 2 will be wired to the BMC.
Right.
And BMC will monitor the error pins, and if they get asserted, BMC will go and handle the RAS events.
Yeah. So the question is for Cooper Lake reference platform, would you wire it to BMC, or keep the current setup?
No, even today it's being wired.
Even today it's being wired
yeah.
to BMC. Okay. Yeah. Okay. So I have another comment is that having OOB to to handle the hardware SMI is good, but have you considered the latency? Let's say like the BMs, right? When the hardware SMI happens, it's normally a serious event, right? The host side needs to know as soon as possible. Now you have it to trigger to BMC to dealing with it. Then there's a latency. BMC has to somehow inform the host side. So what's your considering on that aspect?
So I'm not sure if I fully followed the question, but you're saying that going through the BMC adds latency?
Yeah, because BMC needs to have the knowledge. So two things, right? BMC needs to have the knowledge of the SoC, right? Today, the BMC software in general does not have any knowledge about the host SoC design. This is one thing. Second thing is for BMC to handle it, then BMC, after BMC handling, BMC needs to somehow either notify host or host ask BMC for what happened, right? So that would involve a latency.
Yeah. So if you're going to this model here, right, for handling these things in out of band, that'll require some more architectural work to make it happen. Yeah. So, but today we are talking about the software aspects of, right, the software SMIs today. But we can probably discuss more. We'll be there in the OSF room, Salon 5 and 6. So please come by and we can talk more about it. Yeah.
Hi, quick question here. So for the case study you've given is for the correctable, and does that plug well into the existing EDAC driver? You mentioned earlier EDAC driver kind of has embedded its own translation logic, but with this mechanism, would that plug in well?
Yeah, so with this mechanism, you can do the firmware first model of error handling using the API infrastructure in ACPI, right? EDAC drivers, they want to call into, they have their own translation logic today, but right now we are adding an interface, a new DSM that the Linux community wanted so that they can offload the address translation part to the BIOS.
Yeah, for the EDAC driver for memory correctable specifically, we use like the CMCI.
Right.
So then it will interrupt the core directly, so bypass the SMM.
And then you call into DSM to get more information about the error.
Right.
So that DSM can be moved to a PRM.
Is that available today, or like so? If you call DSM, you will exercise the PRM here, right? So is that available today, or is like how far away are we to implement something like that?
So we are targeting this probably in next couple of generations.
Okay, like Cooper Lake time frame?
The main reason is we want to get this driver, the bridge driver, upstreamed into Linux, right? And then we are working with Microsoft to get it into Windows as well.
And this will be part of the ACPI driver?
Right.
Okay, cool, thanks.
Thanks.
Of course. Before my topic. So Sarathy, on the update side, do you see the Redfish host interface helping? Especially as we're putting root of trust and the BMC and the host firmware as part of the root of trust, wouldn't that be a secure model that you go through a Redfish host interface for the updates?
Can you please repeat the question? I got distracted. So.
I'm saying for the capsule update path, wouldn't it be good to leverage in future the host Redfish host interface that's coming along?
Yeah.
And use that and avoid the SMM dependency.
Right.
And because you have those devices as part of your root of trust, so it's probably a more secure path anyways.
Yeah. Okay. Thanks. Yeah, that's a good point.
Any further questions?
All right.
Thank you very much.
Okay, thanks. So, thank you all. And so we'll be out in the room, Salon 5 and 6, I think. So please swing by if you have any more questions. So, thanks.